Okay, well today we're going to continue our discussion of molecular orbital theory. Remember last time we looked at the p orbital and the different phases of it, and the part of it that's a node where the two phases cancel out. Today we're going to pick up on that and develop it more. So let's continue our discussion of MO theory by looking at this molecule here. Here we have a carbon-carbon double bond, just a single small molecule of ethene. What we're going to do is focus in on the pi bond of ethene, where, remember, the pi bond is equal to 2 p orbitals. Two p orbitals overlapping sideways. So let's go ahead and draw 2 p orbitals that are overlapping sideways. Okay, so here's 2 p's, and remember we have the phases associated with these p orbitals. Well, one way that we can show these phases is for both phases to be on the same side. So we're saying that these 2 p orbitals are overlapping in phase. And when they overlap in phase, we create a molecular orbital slot for our electrons that we're going to call a pi bond. Well, what's another way to overlap 2 p orbitals? Another way is to overlap them out of phase. You see that? When we overlap them out of phase, you can imagine that's not going to be good, is it? Okay? Because these two phases don't match. And so as a result, it's going to cost us some energy. So that energy level for these two overlapping is going to be at a higher energy than that. And if you note, when these two try to overlap, a node forms, doesn't it, between the 2 p orbitals. And so here we learn an important property that as we introduce nodes in between p orbitals, the energy of that slot starts to increase. And this slot here, we're going to call pi star, put a star there, showing that this is anti-bonding. Okay, because we have this node here. Down here, the 2 p orbitals overlap in phase. And so this is our bonding level. Okay? So here's our introduction to anti-bonding and bonding, pi and pi star. Remember that this pi bond has 2 electrons in there, so I put them in the lowest energy level first, okay, according to the off-ball principle. They're paired up, and so they're both down here. There's a little gnat flying around the room, so if you want to bear with me here. Okay, so this is our molecular orbital setup for one single pi bond, okay? What we now want to do is expand this to looking at 2 pi bonds. So let's look at this diene here. Okay, we have two double bonds that are conjugated with each other. And so here we're going to have what? A total of 4 p orbitals, aren't we? So let's draw 4 p orbitals. With all 4 p orbitals overlapping in phase. And so as you can imagine, this will be our lowest energy p orbital, or set of p orbitals for our molecular orbital. And now what we'll do is start to look at them overlapping out of phase a little bit. So what we want to do is create one node as we do that. And a way to do that is to have the 2 internal ones overlapping out of phase, but the external ones both overlapping in phase. Okay? So we've created one node, and that one node has cost us some energy here. Okay? So if I want to make my next set of p orbitals having what? 2 nodes, it would look something like this. To create 2 nodes, one here and one here, I have my 2 internal p orbitals overlapping in phase, but the external ones being out of phase. So let's show our 2 nodes that we have created there. And of course that costs us even more energy. Well, there's one more set of p orbitals to look at. And in this set here, what would we have? Yes, a total of 3 nodes where they are all overlapping out of phase. And so here, all 4 of them alternate. And so we have a node here, here, and here for a total of 3 nodes. And so this MO level will be the highest energy. So here we can call these levels pi 1, pi 2, pi 3, and pi 4. And with 4 p orbitals, this gives us 4 electrons to put in these slots. So they would go 1, 2, and 3, 4 as I continue to build up in energy. So you will want to memorize these 4 orders of p orbitals, just like you want to memorize the one we did before with 2 p orbitals. Here we have some extra definitions. We say that this energy level that has the highest level with electrons, this is what's called my Homo level. Okay? And the energy slot right above it with 0 electrons is what's called the LUMO level. Okay? So these are 2 acronyms. What do they stand for? Write it down. HOMO means highest occupied molecular orbital. Highest occupied molecular orbital. It's the highest one with electrons in it. LUMO stands for lowest unoccupied molecular orbital. Lowest unoccupied molecular orbital. So it is the lowest one with 0 electrons in it. Okay? Lastly, how do we label the anti-bonding and the bonding? Let's take a look here. These four are all in phase, so this is bonding. The next level, I got a bonding here and a bonding here, but an anti-bonding here, so two bondings overcome one anti-bonding. So this is still bonding in nature. Up here, I have anti-bond, anti-bond, and one bond. So now my two anti-bondings are more than bondings, so we'll give that a star for anti-bonding. And then up here, it's all anti-bonding, so that gets a star. Okay? So we're able to label both our bonding and anti-bonding levels. Okay? One last thing we can do here, if we take this set of molecular orbitals and we apply H nu, which stands for ultraviolet energy, what happens is we redraw these four here. What happens is we get a little shift of electrons. When we add energy, it causes one of the HOMO electrons to go up to the LUMO level. So we get a promotion. So that electron goes up there. And here, when we do this, when we apply energy to get that to a higher state, this set of orbitals, these are what's called the excited state, whereas over here, these are all in the ground state. Okay, so we get the excited state when we apply UV energy, symbolized by H nu. And by doing that, we get a shift in the HOMO level. Now our HOMO level is pi 3 star, because it's the highest with an electron. And now our lowest with 0 electrons, the LUMO, is now pi 4 star. So make a note of it. When we go to the excited state, our HOMO and LUMO levels shift to a higher energy level. And so, for example, our HOMO level here would look like these p orbitals. Our HOMO level in the ground state look like these p orbitals. Our LUMO level in the excited state looks like these 4 p orbitals. Our LUMO level in the ground state looks like these 4 p orbitals. Okay? So make a note of that, because on the exam I will ask you to draw the shading of p orbitals for HOMO LUMOs in either the ground or the excited states. Okay, so with this theory here, there's one more that we want to look at. And we'll go back to a regular double bond. but this time we will put it on a carbonyl. Okay? So a C double bond O, we'll be studying carbonyls in more detail later on in chemistry in chapters 18 and higher, and when we start spectroscopy a little later. But a carbonyl is a C double bond O, and we have 2 lone pair on the oxygen atom. Now we want to draw the molecular orbital picture for the carbonyl, and what we get is like we had before with a regular carbon-carbon double bond. We get a pi level, or the bonding level, where the 2 are overlapping in phase. And we get the pi star level, where they are overlapping out of phase. So our 2 electrons would go down here in the bonding level. But here we get something extra. On the oxygen note, we have 2 lone pair. Okay? We call them lone pair, but another name for these are what we can call non-bonding electrons. Why is that? Because they are not involved in the bonding, but they are there on the oxygen. So where do these go in this picture? These go right in between. And we call those the N level, and we have 2 electrons in each. And so we put those there. Okay? So this is what a carbonyl looks like in its molecular orbital theory. The N level is a higher level than the pi, but it's lower than the pi star. Okay? Now you might ask, why have we gone through all of this nonsense, okay, to understand molecular orbital theory? Why did you put us through such torture to get all these p orbitals straight? Well, we did it because we're now going to apply it to a particular topic, which is the last topic in chapter 15 of Wade. And that topic deals with what's called UV spectroscopy, or what's called ultraviolet spectroscopy. So, what does UV spectroscopy look at? Okay? Okay, what it basically does is it looks at double bonds in molecules. Okay, we're going to go back after this material later on and look at other forms of spectroscopy, such as NMR and IR and mass spectroscopy. But what spectroscopy does in general is it looks at different features of a molecule to help us identify what the molecule is. And what UV spectroscopy does is it looks at double bonds within a molecule. Okay? So you can write it down. If a molecule does not have double bonds, that molecule will not show up in UV spectroscopy. Or to put it another way, if a molecule does not have double bonds, it will be dead to UV spectroscopy. It will be dead to it. Just like if you were not thirsty and I gave you a glass of water, you would be dead to that glass of water. You would not want to drink it. So how does UV spectroscopy work? Okay. Well, let's go back, for example, to our butadiene case. Okay. Remember all four combinations of the p orbitals. Okay. I'll let you look back in your notes to see the different shadings. But here were our four molecular orbitals. And here were our electrons in pi 1 and pi 2. What does UV spectroscopy do? When we put a molecule in the UV spectrometer, what happens is the machine blasts the sample with UV light. And when it does that, and I have double bonds, it can promote one of the pi 2, or the Homo level, up to the Luma level. And we call this kind of transition a pi to pi star transition. Okay? And what the machine does is it's able to sense when that transition takes place, and it's able to record that as a type of peak. Okay? And the way these kinds of peaks look like are something like this. They're printed on a graph where you have the A, which stands for, not a grade, but stands for the absorbance of the peak. And then it plots it based on the wavelength of the peak that we'll talk about in a little bit. But suppose we did 1,3-butadiene in the UV spectrometer, we might see something like this. Okay? That's the way these peaks generally look like a blob. And we record that peak at what is called lambda max, which is simply the highest part of that peak. Okay? Then we record that, and then that's part of our data. Okay? But that's what we look at, are pi to pi star transitions in these molecules. Okay? So if I have double bonds, I'm going to see this in there. Let's look at a comparison here. Recall we just did the spectroscopy for 1,3-butadiene. Okay, so there are my Homo levels and Luma level once again, all my molecular orbital levels. But now, what we're going to do is compare it to a molecule like this. What's the difference between the two? Obviously, this one here has many more conjugated double bonds. when we have an increased number of conjugated double bonds, something special happens. Here we have what? 1, 2, 3, 4, 5. Our number of molecular orbitals is always 2 times the number of double bonds, so we would have 10 molecular orbitals here. And our Homo and LUMO levels would be right in the middle. I'm not going to draw out all the different phases, that's not important. The important part that you should be seeing here is that the energy gap, what happens to the energy gap when I get more conjugation? It gets smaller, doesn't it? Okay? So make sure you record that in your notes, that the energy gap decreases as I get increased conjugation of double bonds. Well, remember from physics and general chemistry, that we have a relationship between energy and wavelength, that what the energy is inversely proportional to the wavelength. Okay? So we can show that with this here. So what does that tell us? That says if I have an increased energy gap, that's going to make my wavelength smaller. Or conversely, if I have a smaller energy gap, like I did over here, that's going to make my wavelength larger, isn't it? Okay, so this is a very important property here. Okay, so you can remember it like this, or remember it like this. Just remember if one's high, the other is low. So how's that going to apply for these two molecules? Okay, well, let's draw what we would get then. So let's label our molecules A and B. Okay? So B has larger amount of conjugation, so its energy gap has what? Decreased, so its wavelength should do what? Increase. So B would have a UV spectrum something like this. If I compared it to A, A would be at smaller wavelengths, right? Because its energy gap was bigger. Okay? So this is the first relationship that you need to understand. As I increase conjugation, my wavelength, my lambda max, goes to higher values. Okay? Let's look at one last property of UV spectroscopy, and then we'll call it a day. Let's go back to our carbonyl molecule. carbonyl bond. Remember, if we have a carbonyl, that we had an extra level in here. Okay. Remember, we had the pi for bonding, N for non-bonding, and then the pi star for the anti-bonding. And we had these electrons in these levels. Okay? Well, if you look for the carbonyl, what kind of transitions can we have here? Well, we can have two transitions, can't we? We can have one that is a pi to a pi star, and then we can have another that's what? An N to a pi star. Okay? So the carbonyl can give us two different types of transitions. And as you might expect, in UV spectroscopy, we see those. Which transition do you think will be at the higher wavelength? It will be what? The N to pi star, won't it? So for the N to pi star, that's going to show up down here, and the pi to pi star will show up at smaller wavelengths because its energy gap is bigger. Okay, so we see something like that. How could we apply this to chemistry in terms of doing chemical reactions? Because that's what a large part of organic chemistry is. Let's take a look. Let's suppose we did a reaction like this here. We'll learn how to do this later on in the semester. But we can easily convert a carbonyl to an alcohol using things like sodium borohydride, lithium aluminum hydride, and some other things. But suppose I wanted to see if I did that reaction by using UV spectroscopy. What would I observe? Well, what would I do is I would put this in the UV spectrometer and I would see something like this. And so the spectrum before the reaction would show me these peaks here. Okay. What would I see after the reaction? Well, does the molecule have any double bonds after the reaction? No, there's no double bonds, are there? So what would you see in UV here? You just see a flat line, okay? So both the pi to pi star and the N to pi star would disappear. So this is a way that you could use UV spectroscopy to monitor your reaction, okay? This is how we monitor, okay, to see if the reaction has gone to completion. What would you do? You'd keep looking at the UV spectrum. What would happen with time as the reaction occurs? These peaks would do what? Get smaller, 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 smaller. How would I know when I'm done? When I would see a flat line. Okay? So We'll look at more monitoring reactions when we talk about other spectroscopies, but this is a neat little introduction. So we will stop here for today.